Hello, welcome to Chapter 7, homework questions 14 through 19. Question 14, sketch the shape of the graph of the function y equals b raised to the x, given each of the following values of b. So on A, it wants b is a number larger than 1. So what we have learned that if a b value is larger than 1, then the exponential function will grow, will increase. And so if b is larger than 1, the graph will look something like this, where the graph is increasing. On b, if the b value is a number between 0 and 1, then the multiplier is between 0 and 1, which means the value is going down. And so therefore the exponential function will be decreasing. So something like that. And then for part C, if b is equal to 1, then 1 is just being raised to a power over and over and over again, which would always be 1. So it's just going to be a horizontal line, and this one would be at 1. And so those are the three shapes of the graph for an exponential function for values that are greater than 0. You see an increase, a decrease, and then one that is constant, staying at the value 1. Question 15. For parts A and B, find the recursive equation in A sub n form for each sequence. In the math notes box in lesson 5.3.2, it talks about the form A sub n if you forgot. Part C and D, we're going to do the explicit equation for that sequence. So on part A, we're given the sequence 108, 120, and 132. We have to figure out before we do anything is what that pattern is. So how do we get from 108 to 120? Well, one of the ways is we could add 12, and you can see that once again if we add 12 to 120, we do get 132 as well. So that looks like we have found the pattern. Now we want to write the recursive equation. Well, a sub n plus 1, which would be the next term, is equal to the now term, so this is what we know now, and then if we add 12 to that, then that will get us that next term that we're looking for. We also need to indicate what one of our terms is, which is a sub 1 is 108. So all of that is part of the recursive equation that we need. We need how do we get to the next term, but also remember what is one of the terms in the sequence. So let's go ahead and try that again for part B. So for part B, we're dealing with some fractions here. So we have 2/5, 4/5, and then 8/5. So what's going on? Well, you can see the top, the denominator, you actually see that stays the same, it's 5, but the top is being multiplied by 2. So to get from one to the other, you're going to have to multiply by 2, or 2 over 1, because we don't want the denominator to change. So 2/5 times 2 would be 4/5. 4/5 times 2 would be 8/5, and so on. So this one's multiplication, which means it's geometric. So when we go to write this one, we're still going to start it the same way. A sub n plus 1 is equal to 2 times the previous one. So I'm going to do 2 times a sub n. So every term, to find the next term, we multiply by 2. Once again, indicating what one of the terms is. We'll do the first term is 2/5. Now, for C and D, we want to do explicit, which means we want to write an equation that works for any number of term. We don't want to have to find the previous every single time that we do it. So on this one, we have 3,741, 3,702, and 3,663. So what is happening here? Well, if you look, to start off with, let's see if it's arithmetic, which means addition and subtraction. So it looks like we're adding negative 39. Does that same thing occur on the next one? And it does. So it looks like we are looking at arithmetic. So remember, this is our first term, this is our second, and this is our third. So with an explicit, we need term 0. We need to know what that initial one is, so we can work backwards by adding 39 to 3041. 3,741. So if we add to get to that next one over here, because we're working backwards, that would be 3,780. So we're trying to find that first term. Now that we have that, now we have the first term and the common difference, so we can write the explicit form. So T of n is equal to negative 39n, because that's what's happening. You keep adding negative 39n plus your initial term at term 0, 3,780. And if you chose to write it with the initial term 3,780 and then you're subtracting 39 times n every single time, either one of those is fine. Alright, let's go on to D. So we have 117, 23.4, and 4.68. So what are we looking for on this one? This one, because of the decimals that showed up to me, is going to be something that is being multiplied. So to work backwards, I want to figure out, 117 times what is going to give me 23.4. So I'm going to take 23.4 and divide by 117. And to get a value of 0.2. So is it true that if we take 23.4 and multiply by 0.2, do we get 4.68? And that is correct. So we're multiplying by 0.2, 0.2. So once again, we need to know what that initial is. So we're going to work backwards and divide by 0.2 and get an initial value of 585. So we have the initial, we have the multiplier, so we should be able to write the explicit equation. T of n is equal to my initial 585, and that each gets multiplied by 0.2 over and over again, so 0.2 raised to the nth power. So that's the difference between C and D being explicit and A and B being recursive. On question 16, write the multiplier for each increase or decrease described below. So if something is going to increase at 25%, remember, all of these we're starting, it's increasing 25%, but we start with 100%, and so if we add 25%, that's 125%. But as a multiplier, we want to know what the decimal form of that is, and that would be 1.25, because the percent is out of 100, so it's 125 divided by 100. B, it says a decrease of 18%, but once again, we're starting at 100% and we're decreasing 18%. So that's 82%. 82 out of 100 is 0.82 as the multiplier. Now, is it necessary to show all that work? No, but once again, it gets you the idea as to what you're actually doing. So an increase of 39%. 100% is the original. You're increasing it 39%, so that's 139%, or 1.39. And then D, a decrease of 94%. So we will be subtracting 94, which leaves us with 6%. 6 out of 100 is 0.06. Question 17. E. Hannah's volleyball team left their egg salad sandwiches sitting in the lockers over the weekend. When they got back on Monday, they were moldy. Perfect, said Hannah. I can use these sandwiches for my biology project. I'll study how quickly mold grows. Using a transparent grid, Hannah estimated about 12% of the surface of one sandwich had mold on it. She threw the sandwich out. For the rest of the week, Hannah came back when she had time. Each time she measured somebody else's sandwich and threw it out. She collected the following data. So you see the day on top, and some of them have repeats because she's looking at different sandwiches on the same day, and then you have the percent of mold on the bottom of the table there, your dependent variable. So we want to create a scatter plot and sketch it. Is a linear model reasonable? So to create your scatter plot, there's not going to be a whole lot here. Not a ton of data points on this one. So I went ahead and created the scatter plot, and if you do this on the graphing calculator, obviously it'll look a little bit better, and even on graph paper. But the question is, is a linear model reasonable? Well, if we really wanted to know, we would look at the residual plot. But from what we have, it looks like maybe a potential line could make that fit well, the data fit well, or maybe if I kind of starts to do a little curve here potentially as well. So really kind of depends on what you're looking at. The graphing calculator will show you a little bit better of a model. So from this, we'll say that a linear model is not the most reasonable. Maybe a curve regression line would be better. Part B, based on the story, what kind of equation do you think will best fit the data? So now we're looking at the story and not necessarily just at the data. And if you think back to potentially Chapter 1, this growth is similar to what we did with the flu outbreak. And so it looks like it's potentially an exponential growth in terms of the mold. And then the last part C, fit the data with an exponential model and write the equation. What % of a sandwich did Hannah predict was covered on Wednesday? And consider the precision of Hannah's measurements when deciding how many decimal places to use in your answer. So once again, using the graphing calculator, we can do the exponential model. And if you do that, you will get an equation of M, which represents the percent of mold, is equal to 8.187 times 1.338, and then we'll raise that to our independent variable, which we'll call D for days. So that would be the curve regression line for exponential that you would have got on your calculator. And then if we want to make a prediction for Wednesday would be day 3. So we would take day 3 and plug it into our model to make our prediction. And if you calculate that, you will get a mold percentage, and all the percents are rounded to the nearest whole number. So we'll round this to the nearest whole number, and we'll get 20%. So Hannah would predict the mold covered 20% of a sandwich on Wednesday. And so make sure you answer the question, and also make sure that it is a prediction still. It's not something that's exact. Based on the data, Hannah predicted the mold covered 20% of a sandwich on Wednesday. Question 18. In 1999, Charlie received the family heirloom marble collection consisting of 1,239 marbles. Charlie's great-grandfather had started the original marble collection in 1905. Each year, Charlie's great-grandfather had added the same number of marbles to his collection. When he passed them on to his son, he insisted that each future generation add the same number of marbles per year to the collection. When Charlie's father received the collection in 1966, there were 810 marbles. So we've got a couple questions we need to answer based on that information, starting with question A. It says, by the time Charlie inherited the collection, how many years had it been in existence? Well, you might need to go back and reread some of that and pull that important information as to when it started and when he inherited it. And so in 1999, Charlie received the marble collection, and there was 1,239 marbles. And it started the original marble collection started in 1905. So that right there will give us the information as to how many years it had been in existence. So we take 1,999 minus 1,905, and that'll give you 94 years that the marble collection was in existence. On B, how many marbles were added to the collection each year? Well, we did say in 1999 there were 1,239 marbles. And then at the very end it says when Charlie's father received the collection in 1966, there were 810 marbles. So knowing those two pieces of information, we can basically find the slope, which would give us the amount of marbles that were collected per year. Now, before I write these two ordered pairs down, T is going to equal the time in years but I want T to equal 0 in 1905. And the reason is because that was when the original marble collection had actually started. So if I use the actual year, then when we go to find the y-intercept, it would be in the year 0, which that's not when it started. So we want to use T equals 0 for 1905. So when I go to set this up in the year 1999, well, that was time 94, because it was 94 years from the initial time frame. There were 1,239 marbles. And then in the year 1966, which how many years, 66 minus 5 would be 61. So 61 years and it was in existence, and there was 810 marbles. And so we should be able to find the rate of change, the change of y over the change of x, and that's going to give us how many marbles were added each year. And so if I subtract 1,239 minus 810, I get 429. 94 minus 61 is 33. Take 429 divided by 33, and that means 13 marbles per year, because it's over 1. So how many marbles were added to the collection each year? 13. Moving on to part C. Use the information you found in part B to figure out how many marbles were in the original collection. Well, now that we know the rate of change, we can now use the equation for the slope-intercept form and plug in the information that we know. I'll choose the second point where y is 810. My rate of change, or how many marbles are growing per year, is 13, times my x value of 61 plus b. So then we can go ahead and multiply 13 times 61 to get 793. And then subtract 793 to both sides to get a b value of 17. So how many marbles were in the original collection? You had 17 marbles in the original collection. Part D. Generalize this situation by writing a function describing the growth of the marble collection for each year since Charlie's great-grandfather started it. So it does want us to write it as a function, and it wants us to use n as the independent variable. So we can do t of n is equal to, we have the rate of change, which is 13, times the number of years since it started, plus the original 17 marbles that were his great-grandfather started with. And then the last question, E. How old will the marble collection be when Charlie, or one of his children, has more than 2,000 marbles? And what year will this occur? So they're giving us an output of 2,000. So we would say 2,000 is equal to 13n plus 17, and then we would want to solve that equation. So subtract 17, that's going to give you 1,983 is equal to 13n. Divide by 13, and we're going to get approximately 152.5 years, and that's from the original start time, which was 1905. So it does want us to know what year will this occur. So we need to include, it's going to take about 153 years to get to 2,000. So we need to add 153 to the original year of 1905. And that's going to give us the year 2058 is when the marble collection will contain more than 2,000 marbles. And so I went ahead and added that on there. So in the year 2058, the marble collection will contain more than 2,000 marbles. Question 19. Copy and complete each diamond problem below. The pattern used in the diamond problems is shown at the right, same as it's been the whole time. So on part A, you have 3.5 and 1/2, so 3.5 and 0.5 if you want to look at them as decimals. So on the bottom you add, and that would be 4, and then on the top you multiply. Now to multiply, you might want to change that 3.5 to an improper fraction. So 7/2 times 1/2 would be 7/4. On the next one, we have the top and bottom, which means we have what two numbers multiply to give you negative 28, but are going to add and give you 3. Okay, so think about your numbers that multiply to give you 28 and see if you can figure out any of those that would give you 3. So it looks like 4 and 7 could give you 3 if one of them was positive and negative. And since I am looking for a negative 28, one of them needs to be negative. And so it's either negative 4 times 7 or 4 times negative 7. If I add negative 4 plus 7, I get 3. If I add 4 plus negative 7, I get negative 3. So I want the negative 4 and 7. And it doesn't matter which box you put them in because you are multiplying and adding. For part C, I don't have the value on the right side of the diamond. So the question is, what is negative 7 plus that value? That would give me negative 15. And if I add 7 to the other side, it would be negative 8. So that means this value over here is negative 8. And if I multiply those together, I get 56. And then D is similar to B, where I need two numbers that multiply to give me 10, and then those same two numbers that have to add to give me 7. So with 10, you have 1 and 10, and 2 and 5. So you can see that 2 and 5 would be the better choice. 10 is not negative, it's positive, so you really could do 2 or 5, or negative 2 times negative 5, but they have to add to give you 7. So that would be a positive 2 and a positive 5.